Hello, I hope you're all starting to join the call. Brilliant. So yeah, just as we're waiting for people to join the call, before we start, just a few little things. If you can keep yourself muted during the presentations and use the chat box if you have any problems or if you have any questions throughout the session, please just pop them all in the chat. The presentations will be recorded, but not the Q&A. So if you do have any questions that you may not want recording, please just ask them. We'll make sure we try and cover as many as possible. The links and materials and key points will be circulated post-event. And if you would like any introductions to the presenters or some of the Greater South East Net Zero Hub, please drop me an email and I'm happy to make the introductions. So I'm not sure how many more people will be joining us, but if we just proceed on today, just to make sure we don't have any delays. Before we start, and while the delegates are joining, let me tell you a little bit about Innovate UK KTN. And again, welcome to Net Zero, Heating for Net Zero, Decarbonising Homes and Buildings and Estates. So Innovate UK KTN exists to connect innovators with new partners and opportunities beyond existing thinking. And this webinar series is delivered as part of a programme, Net Zero Places Innovation Network, which aims to help make net zero a reality in the UK by working with local and regional authorities and agencies to connect, collaborate, share and inform and share experiences, lessons learned to adopt innovation and level up across the UK. So that's why we're delivering this webinar series, but we couldn't do this on our own. This is being delivered in partnership with the Net Zero Hubs, specifically the Greater South East Net Zero Hubs. If you've not heard of the hubs, there's 5 of them located across the UK. They're funded by central government and they provide support for public sector to develop net zero projects to the point of commercial investment. They currently provide support for over 200 strategic projects, which have a value of around £4 billion on a wide range of themes which cover power generation, energy efficient, heat decarbonisation. So wherever you are, if you would like an introduction, please just drop me an email and I'm happy to make that introduction. So the purpose of this webinar is to answer the most common questions and share good practice and experience related to heating and net zero, which today being so cold makes it so vital that we get this right. If you haven't already, please check out the recordings of our previous sessions. I'll add the link to the chat. Well, my colleague Mike will add them to the chat. And just a bit of a heads up, there's a couple of Innovate UK funding programmes that are underway. The first is the Net Zero Heat programme, which I thought was the most relevant for this group. That will work with key partners to overcome barriers that enable faster rollout for decarbonised heat of buildings. So the programme will focus on market demand, green finance and design engineering. The second funding programme is called Net Zero Living, the Pioneer Places programme. So there are 2 aspects to this programme. One is Thriving Places, which is very relevant to local authorities. So it's all about providing support to authorities, their partners and communities to overcome non-technical systemic barriers in scaling and adopting innovation for net zero. So that's quite an interesting one. That's going to be done through 2 phases. So phase 1 is opening, I think it's being published now, and we're doing a briefing event on the 31st of October. So make sure you're registered to that. And the second part of that funding call is user-focused products, so supporting businesses to better understand and respond to the needs, opportunities and barriers that are preventing large-scale rollout of net zero solutions. So that one's not been launched yet, but it will be soon. But the Thriving Places will be having the phase 1 being launched shortly. So my colleague Mike will add in the link if you do want to express, just get added to the mailing list for the latest updates, please register to that. So let's crack on with this episode, which we're looking at technical modelling. Thank you so much for our presenters today. So we've got Ben Davis-Nash from Thamesway Energy, and he'll be presenting on how modelling buildings can support decision making, and Nigel Dent from Connected Energy, who will be talking about optimising renewable and grid services to enable greater electrification of everything, including heat. And then, as I mentioned before, we'll have a panel session afterwards, which will be chaired by my colleague, Mike. So if you do have any questions throughout the presentations, please just throw them in the chat and we'll cover them then. So let's move on to Ben. So Ben, I think I've got your presentation, so I'll just move on to your first slide, and I'll switch myself off and let you crack on.
Thanks, Niall. Much appreciated. So yes, I understand that this is about modelling and local authorities. That's very much the space that we're in. Thamesway, my name is Ben Devnash. I work for Thamesway Energy. I'm an engineer working for new connections to a district network. So what you see on your screen is our district network, our estate, if you will, all the different buildings that we're variously connected to. Now, while I might be an expert on the primary side, you generally tend to have to understand quite a lot about the secondary and tertiary side, or the buildings you're connected to. So considering it's local authorities, I presume a lot of people on this call will be interested in the residential side, and that will be mixed use residential, permitted development ex offices, not a lot of new residential possibly, but I don't know. But the good news for you all is we got sight of quite a lot of those, and we have to model them all for our network. So Thamesway supply to multiple different types of building. It means we need to understand multiple different types of energy. And district energy isn't just like any other DNO where you supply energy and you don't really have to care about how people use it. For DNO, for the district heat networks, we have to understand how the energy is being used. We have to understand the end-to-end design, and it means that we're kind of data junkies at the same time as being slightly skeptical of the modeling that gets produced. So you're going to get a bit of a strange presentation from me in that regard. I'm not 100% convinced that modeling is always useful. But anyway, on the if you skip onto the next slide now. So here you've got just a bit of an understanding of what you're looking at on this screen. The primary side is the energy center in big red, which is in the bottom left of your main screen in there. And then you have district network, what we describe as substations or DNH plates in a lot of different buildings. And then we have a whole mixture of different buildings connected to a lot of retrofit to old offices, commercials, medium and high-rise residential. A lot of those are new and a mixture of new and old, and they all have different systems within them. So we have to be interested in the tertiary side and the secondary side, because the better the design and the install of these secondary and tertiary systems, the better the system as a whole operates. It's back to the original concept of how district networks were supposed to work. Better deltas is quite an important element to this. It equals better efficiencies. When I say better deltas, I mean differences between flow and return temperatures, lower return temperatures primarily. They equal better efficiencies for all the primary plant. They equal better lower losses, lower pumping losses, and better and more effective use of storage. For us and for everyone involved, it's a bit of a win-win-win. But if you have a system that's connected that has one errant bypass or an ill-thought-through retrofit, a lot of that hard work can be quite easily lost. And we only see that when we look at the data, and we only see it if we're looking for it. So just to give you a bit of a background as to how the context of the modelling that we looked for, we kind of see both sides of the energy equation. We have a division that works on sustainable communities, and they give advice to various different people around the borough. We have maintenance services that deal with the supply of all of our generation plant. We have something up in Milton Keynes, exactly the same setup as down here in Woking. I work for the energy division, which is new connections, both supply and the demand side of the equation. We have Thamesway Developments. Thamesway are a developer. So we are an ESCO and a developer. We develop, build, own and operate our buildings. We supply energy to those buildings, to our own and to others, and we also advise on buildings. So pretty much we should be in the know when it comes to energy and modelling. But there's a critical point of this. Although there's a wealth of data available in billing, energy usage, efficiency, operational effectiveness, impact and modifications that people make, the bad news is that unfortunately, there's no one department responsible for gathering and analysing this math of data. A lot of our day jobs is just way too critical. So even we have a blind spot when it comes to validating modelling that gets done. And if we're in that position, then it means a lot of the people that we go to for modelling will also be in that position or worse. And we recognise this, but we're in the process of still kind of resolving that internally, knowing that we've got all this data out there. Makes it quite key to try and make sure that whatever modelling we do gets validated somehow. Now, the question on this is the understanding how proposed interventions and how to model those. So I have to ask the question, what interventions are people thinking about? So I threw down on this slide a few of the things that people might be thinking about in terms of their fabric, their changes that they might be wanting to make. Sorry, can't you go to the next slide now? And onto your next slide if you could. Sorry, I may have skipped across them. So what data is good data? Who has it, and who has good data on energy use? But more critically, I find is who is incentivized to gather this data and share it. And at the bottom, I've got a sort of a throwdown of different people who have access to good data, but who might not necessarily be able to share it with you. Because if you aren't modeling with good data, you're basically wasting your time. So before you can model, you have to have reliable data. And where do you get this? Where do the consultants get their data? If you have data on your building stock, how do you benchmark that against other people's buildings? What's normal? What's good look like? So most people with some money can spend a fair amount on consultancies as their first step, asking them to advise them, what's going to give them the best bang for their buck in terms of what interventions they'd like to make. But a lot of the times the consultancies, they hold that information. It's not necessarily fed back to them in terms of how well their retrofits have been how effective their retrofits have been in actually reducing energy. So you've got a lot of people here. You've got the meter companies and billing companies, HRU companies are a good one. They've got what's described as data lakes of information, but they lack a resource to deal with it. They also lack the context and the end-to-end knowledge of exactly how the HRUs are being used, or what the buildings they're being connected into, what the context is within those. Energy supply companies, consultancies, a lot of these guys, they want to hold on to that for intellectual property rights. That they want to hold on to that information so they can sell it effectively. But again, you've got sustainability managers who have a vast pot of data that isn't necessarily being shared. I think what I'm trying to illustrate here is that there is a lot of data out there, but not many people are sharing it easily with others and putting it into the right context. And I think that's part of the problem that we've got, is that a lot of the modeling I look at, I question it. I have to question what's being done. Now, I've just put up here on the top right just the various different interventions. I'm happy to talk about that, but I'm going to skip on to the next bit, which is, Niall, if you go to the next slide. This is some of the information, just throwing it out there as being different things that we've seen consultants not necessarily get right. So top this to do with acceptable pipe velocities. We tend to find that the consultants and designers oversize pipes, and it's not necessarily a very good thing. But oversizing generally tends to be the way of things. It seems to be that modeling is performed by people whose PI incentivizes them to get the numbers wrong. Don't, for God's sake, make this too small, add a little bit more. And being in the industry, having access to actual data allows us collectively to sort of scope out and question some of the modeling results with some authority. So a lot of the premises that consultant designs and models are based on are fundamentally overestimated. And I'll show you a good example. A diversity curve on the screen. Some of you might recognize it. The one in the UK that tends to be used is DS439. I've thrown up a couple of other ones on there, Redan, the Swedish District Heat Association, and our own data. And it suggests that the peak loads are being far too overestimated by people. And yet that's due to the fact that there's an imbalance in this equation. A lot of people will be oversizing because nobody's forcing them to undersize, because a lot of the oversizing faults occur in the O&M sphere. So what happens when you oversize? You slow flows through pipes, you end up getting furring, you get excessive losses, you get plates failing to get turbulent flow and effective heat transfer. You get pumps that are oversized and are unable to turn down below 30%, so they're running too fast. You end up getting bypasses that are open too much because of this, or you get pumps being deadheaded and breaking and overheating. You get boilers which are sort of oversized and prone to cycling. You get fan coil units that are undersized for the appropriate delta, really, because that's the cost thing, but they're generally oversized for their duty. And the net result is that you can actually, with fan coil units, reduce their flow temperature without adversely affecting the response time. But truthfully, it would be better to get them sized correctly to begin with. And a lot of it stems from load estimates right at the outset, which are incorrect based on real world data, because a lot of consultants don't tend to feed that back. Here's an example of 4 different consultants. I've redacted the names, but they were trying to size something for annual energy loads of 200 apartments. And you can see how much their information coming back to us varies relative to the bottom 2, which are our figures for 2 similarly sized, similarly aged buildings. You can see that the information that people are using at the outset is kind of scarily wrong sometimes. If you go on to the next slide, Niall. So I've decided to work through just a quick one on air source heat pumps. You probably had a module previously on this one where you were talking about it. We had a new energy centre and a reputable consultant. You would recognise the name. They worked through the sizing for this new energy centre for serving a new development. We questioned their initial findings because they had storage sizing that were incorrect, boiler sizing, but mostly the addition of the diversified peak loads of the different buildings. Essentially, the Energy Pro model wasn't built right. So they originally sized at a 1.2 megawatt CHP. We kind of ripped it apart and ended up with something that was a lot more realistic for a 400 kilowatt CHP. The scheme developed and it lost a leisure centre that was a large portion of its low voltage energy load. And again, they were still modelling based on a 400 kilowatt CHP, and we pointed out that the Energy Pro modelling was exporting a huge portion of electrical energy being generated, and it was sort of a not balanced heat power balance that was appropriate for CHP. And it took us to point this out at the 11th hour, the fundamental point that the IPRO didn't account for basic economics. So the consultant at the last minute utterly redesigned the scheme, and they remodeled and then concluded that we needed a single large air source heat pump because of economies of scale. And that's kind of what happens when modeling is carried out by people who don't live this stuff. We live energy all the time. And the initial modeling did improve the COP, and you can see this curve here on the bottom left, which was their orange line. But it's important to work out where and why these models are, and you delve into the modeling behind it. We pointed out that you only needed to hit a certain percentage of carbon reduction target for the scheme, and that to do this, we'd likely be running the air source mostly at night because of the low energy use pricing, and also only at times of the year when the ambient temperatures were over 5 degrees C, and we'd be using the sort of the boilers the rest of the time. And that changed their modeling, that changed their thinking. And also, you can see this grey line. We discovered, or we well delved into it, that the large 200 kilowatt units that were being proposed actually didn't have this orange dotted line in terms of COP. They actually had a COP that was more akin to this grey line, which meant that it was very, very close, in fact, extremely close to these smaller units that we were proposing. They still said that it's better, and therefore you should go for the larger units. The issue being is that they don't live the realities of having reliance on one large unit as opposed to 5 smaller units. So we pointed out that the dynamics really can change when you compare apples with apples. The actual output was pretty appropriately sized for an air source 1/5 its size, and it was better, but not by much. And the linear aspect of the orange line was the real giveaway. And you throw in the real world stuff, the ease of maintenance, the ease of replacement, the standardization and ubiquitousness, if that's a word, of these types of small units versus the fairly bespoke and kind of risky nature of going for one large unit. And we concluded that a sensible operator would go for smaller units. Incidentally, we also managed to cut the number of boilers they wanted to install, because by simply just changing the proposed hydraulic arrangement to allow the boilers to charge a thermal store, again, something the modelling hadn't considered. So although this is a talk about how modelling is useful, it's also a talk for me about how modelling sometimes needs to be challenged, and challenged with some real world experience behind it. A complete side note here, but the lower the return temperatures that you get from your network or building, the more this shifts to the left, and not an insignificant amount either. So I've just sketched on there. I should have made that blue line slightly thicker, but you see how the coefficient of performance drops very significantly when you start running to buildings that are running on high temperatures. I'm sure a lot of you guys already know that. Next slide, if you could. Niall, how am I doing for time?
Yeah, you've got a couple of minutes left.
Fair enough. I'll skip through quite a lot of this. I'm sure the slides will be handed out and you can maybe go straight to the end of some of this, but a lot of the modeling that we get done, we have to make sure that we believe the data that's coming back, and a lot of the Energy Pro and TM46 stuff is a bit fuzzy, and it doesn't have real feedback from clients back to the consultants of whether or not those information is correct. The return temperature is a big issue for us, and it's rarely a consideration at the design stage, but it's something that everyone should think about. The energy sizing, the peak plant, again, they seem to be incentivized to oversize it, and the diversity curves is an example of that, and really wary of that type of thing. Again, there's this bottom bit where you're pre-modeling. A lot of people is incentivized to do a lot of pre-modeling, get the baseline right and make the case, but a lot of projects aren't really incentivized to post-model. There's a time element to it, there's a cash element, there's a desire to move on, maybe even some instances embarrassment about how the system's gone. They rarely get feedback going back to the original designers, and so therefore you end up that mistakes tend to be repeated, and that's a concern, certainly for anyone wanting to do any modeling. Jump onto the next slide now. Could you jump on? Yeah, there you go. So this top one, the generation mix, very few people are in a position where they can play off different plant against one another. But if you're in that fortunate position, that's when you might want to get some modeling done. And that's something that we've been trying to do very extensively. But very few people are in that position. You're pretty much at the mercy of either gas price or electricity price, depending on what's supplying your building. And again, you're also sometimes in the crux of carbon or cost, and they're often frequently mutually exclusive, unfortunately. You can modify your BMS, but you need to know what those interventions, how important they are, and how marginal they are. You can make some real modifications and changes, but you don't actually have a clear understanding if you don't have a good baseline of what these changes are going to do, and how useful it is. Again, a lot of these people will be telling you to put in a lot of sub-metering as your first instance, and I would echo that. Changing measuring the flow, the sub-metering of flow, sub-metering of temperatures, sub-metering of your electricity usage, and getting all that coming onto a historian. That's invaluable. That's your eyes and ears. So let's. I'm skipping through my notes. My apologies. Yeah, it's all about good historians and about how important it is to try and make sure that you have good modelling about how these things go in. I want to skip straight to, if I can, the next slide, which is about return temperatures, which is one of the main pieces that I would like to talk about, which is your return temperatures. If you can get that back onto a constant temperature variable flow system, that's one of the best indicators you can have of how a building's operating. It's a real indicator of how much bypass you're getting, either via the fan coils or air handling, or via the over temperature bypass, and that leads to inefficient pumping, failed valves. It's a measure of how effectively you're using your heat emitters, and whether or not they're balanced right. It's a measure of how efficiently you're using your on-site generation plant or the connected plant. The lower the temperature, the better they are. And also a measure of how effective low carbon future retrofits will be for that building. So it's a lovely rule of thumb really to know what your system should be returning at its design temperature. I get for a mixed constant temperature, variable temperature system, it's a little bit hit and miss, but by switching to a fully constant temperature system, you can get an extremely useful KPI to trend, one which waves a big red flag when something's not right. It's like a big check engine light on your BMS. Here's an example on your bottom left of HRUs, mainly HRUs and a medium rise, and you're getting a very good delta T on that one. These HRUs were initially giving you 45 to 50 on this site. It turns out that they hadn't been commissioned. They were installed supposedly pre-commissioned. Your top right, ignoring the fact that the flow and the return temperature probes are in the wrong place, which the eagle eyes among you may have spotted, you are still getting a fan coil system that's giving you about a 30-degree delta. That's good. That's not bad. You know, you'd want for better, but as soon as you start seeing things where you're, like for instance, the next slide, where you start seeing the delta T's coming incorrect, where you're seeing that gives you a bit of a clue on your BMS that something actually is fundamentally wrong. Again, this is a site where the fan coils and the air handling is all designed to try and achieve a 30-degree delta. You're seeing that you've got a flow imbalance here. You are using more effectively the higher boost plate rather than the low grade plate, which is what you want to be doing. And the only way you get to usefully use that is by returning lower temperatures. And that's appropriate for VRF systems, that's appropriate for air heat pumps or ground source or whatever you want to do. It's appropriate for boilers. It's true across the board. You can see that this site isn't working desperately right, and it's to do with an imbalance of flow, and you can see that there's a bypass. It's actually bypassing too much water and mixing relative to what's coming back from the fan coils. You can skip onto the last slide. So yeah, this is just basically a quick view of all the different I've overlaid some items that we would regard as an idealized secondary and tertiary system, where that's what you should be looking for a well-designed system. If you're looking to change your system, I would suggest respectfully that you want to be iterating towards this type of arrangement. That will allow your buildings to operate better, allow you better control and understanding of how the building's operating, and allow you yourself to do better modeling, or if you prefer to scope that out, give data into the hands of the person who's going to be modeling it for you. Again, happy to take comments or questions on this or any other slide. Did I hit the 10-minute mark?
Not quite.
Not
but
even
that's
close.
Fine. Okay, so next up we've got Nigel Dent. Thanks so much, Ben. Nigel, are you okay to share your screen? And if you do have any questions around that presentation, please just throw them into the chat box and we'll pick them up ready for the Q&A. And in this space, no questions are stupid questions. So please do ask whatever you like. We also have colleagues from the Greater Southeast Net Zero Hub who are on hand as well to answer any further questions around this. So Nigel, I can see your presentation. So are you ready to go?
I am ready to go, yes.
Brilliant. Thanks.
Thank you very much. So yeah, I'm Nigel Dent. I'm head of sales at Connected Energy, and I'm going to talk a little bit about how battery systems can support decarbonisation of heat. So just very quickly, a little bit about us. So we are a battery storage manufacturer. We're based over at Hethel Engineering Centre in Norfolk and up in Newcastle. We've been around since 2010, so we have lots and lots of data around second life EV batteries. We've been running them, since 2012, so around about 10 years. And we've got proven experience in microgrid integration, which is what I'm going to focus my presentation on today. So bringing different technologies together to reduce the carbon intensity of a site. We only use second life EV batteries, so we are basically a reuser, a repurposer, and our battery partners include Renault, Volvo, and Caterpillar. So that's where we get our batteries from. So how do we model battery storage? So we have our own platform called KEMP. connected energy management platform that was it's been built in-house, and that allows us to do lots of different things. It allows us to monitor the life of the battery pack. So we run our batteries in series, so ideally we want the battery characteristics to be very similar. But more importantly, we look at the site parameters. So we can take metering data from any technology that's on site. So if you have solar on site, if you have EV chargers on site, if you have air source heat pumps on site, we can pull in the usage data or the generation data from the renewables, and we can map that. We can then see how a battery storage system could positively affect the site by moving the energy around, by storing that energy from the renewables. Kemp also does lots of other things. It allows us to schedule our batteries, so we can manually schedule, we can auto schedule, we can view and retrieve historical data right down to kind of minutes, hours, days, all the way back to when our first batteries were installed. So we have some data scientists based up in our Newcastle office who are doing a lot of modeling around battery running and how different batteries are performing within an actual container, and to see how we can optimize our systems better. It also allows us to collect real-time data of power and control. So if we're bidding in a frequency response market, we can bid very, very quickly because we're seeing real-time activity on the grid through the aggregator. This platform is available to our customers 24/7, which is really good. And as I say, it's been designed and built by Connected Energy, so it's tailor-made, and we can verify data as well, which is really important. So if we put a battery storage system onto a customer site, it's doing X, Y, and Z, we can then go back and verify that it is actually doing that. So this screenshot here is showing a number of different things. It's showing the battery storage charge and discharge throughout the day. It's showing the solar it's showing the site usage here, and then it's showing how the battery system is offsetting those peaks. So you can see the light blue compared to the green, where this is the natural load without a battery, this is the load with the battery, and then we can pull in other assets. So we can pull in the solar PV data and the solar export data as well. So why would you collect data from a BESS, from a battery storage system? Well, it goes back to what the site is hoping to achieve. So what is the battery energy storage system's function, and how can we monitor that? So a little kind of screenshot here over on the right is, are we looking at EV charger support? Are we doing some peak shaving, which is, offsetting carbon intensive grid electricity? Are we looking at monitoring our system? Are we doing some scheduling for frequency response? So we kind of start at the beginning, where we look at the half-hourly data of a site. We understand what the drivers are, what the criteria is. We understand, is there renewable generation going on site? Understand the heat demand. What is the heat demand of the site? Are they bringing air source heat pumps? Are the heat pumps already in place? Are we looking to offset additional electricity usage from the heat pump? We can delve into the different tariff structures. Are there different carbon tariffs set up on the site? Can we charge at a low carbon tariff and then discharge out its high carbon tariff? Can we match that to low and high cost tariffs as well? Or can we do both? Can we, do multi charge and discharge on a site? And then can we offset that expensive import capacity increase? So we collect all of the data from a customer site, and then we can then kind of provide a model. So this one is looking at renewable optimization. So first of all, we get the half-hourly data. We pull in the half-hourly data from the site, and that gives us a baseline. And we're looking at certain parameters. We're looking at the average daily usage, the average nightly usage, average weekend, what the import capacity is, what the export capacity is, what could a battery actively do here. And then with this site, we then map solar. So we're adding solar generation on here. So we've got the the generation data for existing solar or predicted solar, so new solar coming on. We can map that on there, and then we add our battery system in here, and we can then model the output of the battery. So what is our battery doing? It's increasing the utilization of the solar, it's making that site more self-sufficient, it's increasing the carbon saving, and it's also increasing the energy saving. So we can do lots of different things with our data, the site data and the battery data. And then we can also look at other opportunities, so grid services, so the potential for the battery to sit and support the grid, and we can provide a payback for a customer as well. So I'm just going to go through a few kind of different scenarios of batteries that we've already got out in the field. So we have a battery sitting on a site with Dundee City Council, where we're looking to basically get the site to be as energy self-sufficient as possible. So they have a large PV array, they have a number of EV chargers supporting a taxi fleet, and they want to utilize that PV system as much as they possibly can. So what we've done is we put a battery storage system in, and the battery is charging from the solar, and it is powering the EV chargers as much as possible. So it's powering these 22 kilowatts and the rapid EV charger, which is then offsetting grid electricity. So we're not using grid electricity when the sun is shining, we're capturing the PV into our battery, and then we're putting it out into these EV chargers. And we can monitor this in real time. So this site went from 85% efficient from the renewable optimization, sorry, 85% renewable optimization up to around about 99%. Just a couple of very quick points about the system. So it's a small system. It was one of our first battery storage systems, 6090, a little 10-foot container, as you can see in the top right of the picture. And there's a 50 kilowatt PV array, and it's powering these 50 kilowatt and 25 kilowatt EV chargers. So another project here is active grid load management. So we've looked at it. This is based in Germany. So Allego came to us. They said they're looking to install 2 50 kilowatt rapid chargers, but they've only got a connection limit of 60 kVA. So we pulled in the half-hourly data from the site. We then mapped and modeled what these 2 rapid chargers would do, and they pretty much breach all of the time. So then we modeled our 60 kilowatt, 90 kilowatt hour battery, and we installed that in active load management mode. And this shows what the battery storage system is doing in practice. So we're managing the site load down to 35 kilowatts. So you can see here the natural load is the neon green. So they have a 60 kilowatt limit, so they would breach here, and that could trip the site. So what we're doing is we're maintaining a 35 kilowatt usage by monitoring the EV charging demand and providing the battery power into that EV demand as and when it's required. So you can see the state of the charge of the battery. So we're discharging out into the site, offsetting this peak, and then we're charging up again here when there's no demand, and then charging up, and then we're discharging out again. So this is real-time data that we can monitor, and we can verify that we are maintaining this 35 kilowatt constraint. And this is a third project that we've been working on. So this is low carbon grid load management. So basically, we're providing grid load management for a site where they are constrained, as well as storing the on-site renewable generation. So as in the last project, the Allego one, there was no renewables on site, whereas this one, this is over at Lotus, right next to Hethel, where there's a wind turbine, solar PV generation. They are both creating renewable generation, which is going into our battery. We are then providing load into the EV chargers and also the site. So we're offsetting carbon intensive grid electricity there. Just very quickly about the numbers again. So there's a solar canopy there, micro wind turbine, 4 kilowatt wind turbine, 50 kilowatt rapid charger, and 6 22 kilowatt chargers. So sorry that I'm flying through this, but I'm trying to stay with my 10-minute time period. So we put in rules. So we put rules of the control system. So unless the e-store is fully charged, generation from the PV and the wind turbine would be stored directly into the battery. If the battery is full, then that wind and PV can go directly into the site, and it can offset the site. So we can offer full site integration. So this is our kind of KEMP software again. So we're looking at our control. So we're directly interfacing with whatever technology there is out there. So if it's EV chargers, heat pumps, wind turbines, we can then connect in. We can provide load directly out, and then our software monitors the metering on all the different assets. So if we meter the site load, we can capture all of the half-hourly data, and then we can graph that. We can capture all of the renewable generation, any other generators on site. If there's diesel generation on site, we can offset that with our battery system. We can meter that load. We can pull that in, again, reviewing the data to see how effective that is. What is the site paying for their diesel generators? How much can we offset by using a battery? And this is all being powered by the data. And then we've got our multi-criterion decision making. So what we're looking at the different assets on the site. So PV generation, the load from the EV chargers, are the site load profile, so the unmanaged load and the managed load, and then our energy storage state of charge. So what is the customer looking to do? Are they looking to optimize the PV generation? Are they're looking to provide load to EV chargers 24/7? Is there potential during the winter months when the sun is not shining as much to put the battery within the grid services market, so you can access some additional benefit there? So what we then do as well is we monitor and validate all our data. So as I mentioned, we've got a data team up in Newcastle who are working on our reporting system. So every customer that has a battery storage system, they will have access to a monthly system report that we send out to the customer, and we can show them how the individual battery packs have performed, how they've performed within their chosen functionality. Is there anything that we can improve? Are the batteries being run too hard, or is there high levels of redundancy? So can we work those batteries harder? So we've got a back office, as I say, up in Newcastle that is verifying the data on a daily basis of how the battery storage system is working on a site. So I just wanted to end with a case study where we are supporting the decarbonisation of heat for Cranfield University. So Cranfield Specialist Postgrad University, specialising in sustainability and manufacturing. So they've got a big they've got a big site, they've got 60 transformers, 2,000 sub-meters, a very complex site, private wire network, and they look to us to install 3 battery storage systems, 300 kilowatt systems to help them offset the additional electrical usage of their air source heat pump, but also to utilize their solar farm that they currently have on site. So what we've done is we've installed 3 e-store systems, 900 kilowatts, 1080 kilowatt hours across the site. So they're in 3 different locations. We use a group control device to aggregate the 3 systems together to give them that 900 kilowatts of power, but they can also work individually as 3 independent systems. One of the primary goals, again, is to offset that additional electricity generated by the air source heat pump. So we have metering and data on the heat pump, so we can see when that heat pump is being used and how the battery storage system is offsetting against that. This site is a zero export site, so we can overcome those issues by capturing as much solar in the battery as possible and then putting that into the site load. And again, we've got the data to verify that. Capture the renewables on the weekend to avoid any wastage when their site usage is lower, and then we can put it back out into the site on the Monday. And then we're doing the charging at low tariff and discharging at high tariff. So we're charging at about 3 o'clock in the morning, Monday to Friday, and discharging out at about 4 o'clock in the afternoon for Cranfield. So in essence here, this battery storage system is helping Cranfield to decarbonize their site by allowing the implementation of a heat pump without a massive electricity bill increase, because we're offsetting that with the battery and the solar system. And that is me. Thank you very much.
Thank you, Nigel. That was a great presentation. So we've now hit the end of our recorded sections. So I shall now switch record off and hand over to my colleague Mike, who will be running the Q&A session.